Hold still.
System's looping. No response from the gateway.
We're flushing the cache. Come on,
Error
come
cascade imminent.
Plug it in now.
Rebooting. We have amber light.
People! I want solutions! Now!
There's one person who can help. But he's a legend.
A legend?
John, critical path!
Get him on the line!
This better be critical.
Mr. Path, our servers are down. The whole network's on fire. We need you.
I'll need my tools. And hazard pay.
How much?
100 per hour.
It's just...
I'll take it from here. You don't have a server problem. You have a path problem. You need to implement critical path management.
Wait, what exactly is...
Critical path management? What is the critical path? Let's just say it's my middle name. Allow me to enlighten you. Now, let's trace the path that matters most.
We'll define each activity as a node and arrange them left to right based on their dependencies. Nodes with no or little dependencies will be on the left, and by contrast, nodes with higher dependencies will be on the right. This will simplify the network and help us find the critical path. We'll begin with node A, as it is the first node. Then node B, C, D, E, F, G, H, I, J, K, L. We must add begin and end nodes as well to mark the start and end of the critical path. The critical path algorithm involves two scans, forward and backward. A forward scan finds the earliest possible start time for each task, while a backward scan finds the latest possible start time. We will put the results of the forward scan on the top halves of each node and the results of the backward scan on the bottom halves. Let's start with the forward scan. We will create connections between nodes that have dependencies on each other. Now, referring to the table, assign each node activity with the time it takes to complete it. Looking at the table, A takes 50 microseconds. So, add 50 microseconds beside node A. Do this for each node. B, C, D, F, E, J, H, G, K, I, L. Now, the forward scan can begin. The earliest time for each node is entered in the top half. Let's start with node A. As A is the first node, it takes no time to start it, so it has a value of 0. Next, we do nodes B and C. Remember that we can only determine the earliest start times for those tasks whose predecessors' earliest start times are known. Hence, why we start the algorithm from left to right. As activities B and C can only begin when A is complete, we put 50 in the top halves of both these nodes. Next, we have nodes D, F, and E. D only has one arrow pointing at it and has two predecessors, B and A. Thus, D's time to start is the sum of B and A's time, 400 plus 50, which is 450. We put 450 in the upper node of D. The next node is F. Calculating its time to start is more difficult though, because two arrows terminate at this node. In this case, the earliest start time for this node is the largest value among the length of the paths to this node. So since C has a greater length than D, 5,000 to 1,000, the path to F is A plus C, which is 50 plus 5,000, so 5,050. The last node is E. It only has one arrow, and its path is A plus B, so its time is 400 plus 50, so 450. We apply the same process to the next three nodes, J, H, and G. We calculate for node G, then node H. The next nodes are K and I. We calculate for I, then K, then node L, then finally the end node. Therefore, the minimum time of completion is 10,750 microseconds. The forward scan is complete. To finish the critical path algorithm, we must perform the backward scan. The backward scan finds the latest possible start time for each task. We will enter these times in the bottom half of each node. The backward scan starts from the end node and works backwards. In the instance that more than one edge starts from the same node, the latest start time for that node is the smallest value among the lengths of the paths to this node. The nodes that have the same earliest and latest start times lie on the critical path. Starting from the end node, its latest start time is 10,750. This value is entered in the bottom half of the end node. To get to node L, we subtract 500 from 10,750, as that is the length of time for this task to complete. This produces 10,250. Next is node K, and we subtract 200 from 10,250, resulting in 10,050. Node K has two nodes leading to it, I, 700, and J, 2,000. In this case, we choose the node that has the shortest path length to K, which is I. Thus, we subtract 700 from 10,050, which is 9,350. We apply the same process to node J, then node F, then node C, A, H, G, E, B, and finally node D. To find the critical path, we look at the nodes that have equal earliest and latest start times. These are the nodes in order: A, C, F, J, K, L, and thus form the critical path.
Your computers are not running efficiently. They are ignoring the critical path. And as a consequence, they are dying. If we make your tasks efficient, if we truly follow the critical path, your network will run like a well-oiled machine. Let me explain.
I bet you're wondering, how will the critical path help you? No matter how many computers you have, you can't do everything at once. Some processes simply cannot start until a previous process has finished. If there is even the slightest bit of delay between processes, that can add up to a massive time loss. This is why computer scientists are always trying to make the smallest optimizations in how efficient a task is. Let's look at the example critical path from before, but apply it to a network of computers. First, let's unselect the critical path. Now, we can group these nodes by which computer is performing the task. Each row will be actions completed by an individual computer. Here, the power of the critical path is that you don't need to start certain tasks until absolutely necessary. That means any time a computer is not spending on one of these tasks can be spent on something else. Take tasks B and C, for example. Task C has to start by time 50 to not waste any time. Task B, meanwhile, does not need to start until time 1650. This means computer 2 can perform a different task until time 1650. When you follow the critical path, there will be a lot of available flex time, such as this. However, the wait time for the critical path must be as close to zero as possible. The time it takes to complete the critical path is the minimum time your work will take. To reiterate, the critical path will provide you with some amount of wiggle room to complete other tasks. This is time that can be spent elsewhere. Time not spent on the critical path is time wasted.
All right, everyone, it's time.
Okay, Mr. Path. We trust you.
Ain't going in. Turning.
Let's begin.
Engage the critical path.
Remember, always follow the critical path. That's not our code.
Took you long enough to notice.
Who are you?
I'm Chad of GPT. I'm here to take your job.
Then we're already too late.